Alrighty, so thank you all for coming this evening. Hope everybody is doing well. So we're going to jump right in to something that's relevant to your homework that's coming Thursday. So we're going to jump into energy and power signals. So energy and power signals are properties of the signal, and it's important to know that a signal can be either a power signal, an energy signal, or neither, and it is defined based on the equations on the left. These equations, feel free to take a picture of them or write them down, but these slides are also available on the Canvas if you need to refer back to them later. So the way you determine what type of signal a signal is with these equations. So if you calculate out the energy as a finite number, then that means that the signal is an energy signal. And if you calculate out power as a finite number, then that means that it is a power signal. And if you get that power is equal to 0 and energy is equal to infinity, then it is defined as neither a power signal nor a energy signal. And one important thing to note is pretty much all periodic functions, so pretty much all sinusoids are going to be power signals. And an example of an energy signal versus a power signal. So the power signals, think about like your AC function generators that y'all have used in circuits in the past. Those would be power signals versus an energy signal would be like a square wave pulse. And then we're going to go ahead and jump into solving a problem. So determine the energy and power of the following signal. So we're going to use the equations from the slide before, and I'm actually going to jump over to screen sharing on my iPad quick so we can get into this. Alrighty. So I have the problem written out here. So we're going to utilize this to find our energy and our power. So our equations are given, both the signal equation and the equation for energy and power. And also, quick note, feel free to stop me at any point if you have a question. I'm about to jump into a whole lot of math. So if you have a question, feel free to just interrupt. But we're going to utilize these equations. So first, we're going to calculate our energy. And I would recommend to always start with energy, and you'll see why later. But so we're going to have energy is the limit as t approaches infinity of the integral from negative t to t of the absolute value of cosine 2t times step function squared dt. Oh, I forgot. Have y'all learned about step functions yet? Go ahead and drop it in the chat
Not
or just let me.
exactly. We just did like piecewise functions.
Okay, so I will explain those quickly before we get into this. So a step function is basically just another way to write a piecewise function. So the definition of a step function, it's always written as u of t. And you have your graph. So you can decompose, I'm going to move this over here. You can decompose this into a piecewise function, and it's always defined as u of t is equal to 0 when t is less than 0, and it's equal to 1 at t is greater than or equal to 0. So it's going to look like this on the graph. So it's going to be 0 here in the negative x region. And then once you hit 0, it's going to jump up to 1 and then continue on to infinity, unless otherwise defined. You will learn more about them later. They can be shifted. You can have two of them where it turns on and off. But for this particular problem, all you need to know is that u of t represents a step from 0 to 1 happening at 0. So we're going to jump back into this. So we're going to use this. So we have limit as t goes to infinity from negative t to t. And then the absolute value in this case is applied to the function at the beginning. So for example, if you had a negative function, you would make it positive and then square it. Because this function is already positive, we can just go ahead and ignore it. And then we're going to apply the square. So we're going to get cosine squared of 2t times u squared of t dt. And now we can get into how the step function comes into play here and why you need to know it. So based on the bounds of your step function over here, it's always going to be 0 when it's less than 0 and 1 when it's greater than 0. So you can apply those bounds to your integral over here. So this, when t is less than 0, it's equal to 0. And when t is greater than or equal to 0, it's equal to 1. And then because 0 squared and 1 squared just remain the same, you can kind of ignore this squared. And you can use this to say, okay, when we're at t is less than 0, we're in this domain. This function, because it's multiplied, is always going to be 0. And then when it's in this domain, because it's 1, you can just rewrite this term as 1 times your cosine squared. And you can use this to actually change your integral and change that lower bound from negative t simply to 0. Because any value less than 0 is always going to be 0 because you have a step function multiplied in. And any value greater than 0 is always going to be 1. So then you can treat it as if there is a 1 here times the cosine squared term, and that simplifies the function considerably. So now you're really just left with the limit from t to infinity of the integral 0 to t cosine squared of 2t. Now, we're going to use some trig identities here to rewrite this in an easier format. So we know that sine squared of x plus cosine squared of x is going to always be equal to 1. And we know that cosine of 2x is going to be equal to cosine squared minus sine squared. And we can rewrite this to find a form of cosine squared 2t that is easier for us to solve in this integral. So if you rearrange this bottom equation, so you move the sign over to the left side of the equation, you get sine squared of x plus cosine of 2x is equal to cosine squared of x. And then you subtract this cosine over. You're going to get sine squared of x is equal to cosine squared of x minus cosine of 2x. Now you can substitute this sine squared back in to the first identity that we addressed, and it's going to simplify down to 2 cosine squareds minus cosine of 2x is equal to 1. And now we can rearrange this to find a value of cosine squared. So we get 2 cosine squared is equal to 1 plus cosine of 2x. And then we're going to divide that 2 over. So now we don't have an x term in our equation, but we can consider this 2t as our quote unquote x term and substitute it into the equation down below. So we're going to rewrite our energy equation. as equal to the limit as t approaches infinity, the integral from 0 to t, and then we're going to substitute, we're going to change our cosine squared of 2t into the format that we just solved for. So we're going to get 1/2. I'm going to pull the 1/2 out from this just to make it simpler, times 1 plus cosine of 2 times our x value, which we defined up here to be 2t. Now that we're in this form, the problem is considerably simpler to solve. So we can, the first thing we're going to do is we're going to pull the 1/2 out front. Our bounds are still 0 to t. And we're left with 1 plus cosine of 4t. So now we can integrate this. And we're going to be left with t plus 1/4 sine of 4t. And in order to solve the integral of cosine of 4t, you just need to do a simple u substitution. But then we're going to evaluate this from 0 to t. And we use our fundamental theorem of calculus knowledge that I'm sure we all love from Calc 1 to solve for. This is going to be t over 2 minus 0 over 2. So we can cross that out. That goes to 0. Plus 1/4 sine of 4t minus 1/4 sine of 4 times 0. Now, because this is 4 times 0, this is going to be equal to 0, and sine of 0 is 0. We can go ahead and cross this out as well. And that's going to leave us the limit as t approaches infinity of t over 2 plus 1/4 sine of 4t. So now we need to evaluate, okay, what happens as we approach infinity? So let's start with the sinusoidal function. So this function, as it approaches infinity, because it's sinusoidal, it's going to be periodic, and it's going to simply bounce between two values. Oh, I apologize. This should be 1/8, not 1/4, because of the 1/2 up above. It should be as well. So it's going to bounce back and forth between 1/8 and -1/8. So we can say it is finite between -1/8 and 1/8. It's always going to be between these two values. And then our t over 2, we can substitute in infinity over 2. And that's just going to remain as infinity, because infinity over 2 is just equal to infinity. But we can say that the energy equation is equal to infinity over 2 plus or minus 1/8. And we can cross out the over 2 and the plus or minus 1/8. And you're just left with infinity. So we can say that the energy of that signal is equal to infinity. So that, by definition, as we stated before, makes it not an energy signal. Because to be an energy signal, your energy has to be a finite number. So now, real quick, does anybody have any questions? I just did a whole lot of math. I want to make sure everybody's on the same page. Go ahead and drop them in the chat or just unmute yourself and say something. I'm happy to jump back to any point in that. All right, I'm glad to hear it. All right, anybody else have any questions? All right, I'm going to go ahead then. If you have any questions, feel free to interrupt me at any point. So we know that our E infinity is equal to infinity. That means it is not an energy function or an energy signal. Now we have to evaluate power. And this is made easier because we've already evaluated our energy. Because this part of the equation is identical. So we can substitute in our equation for energy. Now, it is important to note, we don't want to sub in our final answer down here. We don't want to just sub in infinity and try to multiply it out. We want to plug in our equation that we were given up here. So in this particular case, we're going to substitute back in our t equation after we evaluated the integral. So we're only going to sub in this part of the equation down here.
If I may jump in real quick, Ryan. So
Absolutely.
if you don't mind scrolling back to the where you wrote down the E infinity or P infinity in terms of E infinity.
Mhm.
So most books will write it like that. What I try to do is instead of E infinity, I just call it E of T. That way we know that we haven't plugged in T equals infinity yet.
Okay.
But the way you've written it, I think I've probably seen that in multiple textbooks. So that's not a wrong way to put it.
So you'd prefer it in that form?
I prefer in this form just so that we are, it remains that way you're reminding everyone that, hey, it's the same expression for E. We just haven't plugged in the T goes to infinity yet because the limit is still to come.
Absolutely. Okay, that makes sense. So we can plug in the equation that we got down here after we evaluated our integral. So we get t over 2 plus 1/8 sine of 4t. So we're going to get our power is equal to the limit as t goes to infinity of 1 over 2t times t over 2 plus 1/8 sine of 4t. And now we can simplify this expression. So we're going to multiply in our 1 over 2t. So we get limit as t approaches infinity. And our first term, we get t over 4t. Our t's cancel. So we're left with 1 over 4. And for our second term, we get 1 over 16t times sine of 4t. So now we're going to plug in infinity. And the first term is just 1/4. It's a constant. There's no t term. So 1/4 is unaffected. And in our second term, so we have to take this in two parts. So what is our sinusoid going to do? Just the sine of 4t part. It's always going to be a bounded finite value. So we can consider this part as finite. And then when we plug in a t to the 1/16t, we're essentially 1/16t, plug in infinity, get 1/16 times infinity, which we can approximate to 0. So we're basically getting 0 times some finite number in every value of t, or sorry, as we approach infinity. So we can consider this to be a 0 term. So we get 1/4 plus 0, and our power is finite, equal to 1/4. Now we can come up here, power equal to 1/4, which means that this is equal to a power signal. So we've calculated the power and the energy for this function, or for this signal. And we've concluded, based on the statements we made earlier, where if our energy is a finite number, it's an energy signal. And if power is a finite number, it's a power signal. Because we got energy is equal to infinity, it can't be an energy signal. But we did get a finite number for power, which means it must be a power signal. Does anybody have any questions? I am happy to jump anywhere, address anything. And keep in mind, the recitation slides, as well as all of the TA notes, will be posted along with this recording. So please ask questions now, but if you need to go back later to understand further, feel free to do that as well. Can I give a few more examples of power G and energy signals? Real life examples. So power signals are going to be any sort of sinusoid generally. So really any type of AC current is generally going to be a power signal because it's a sinusoid, whereas energy signals are more common as pulses. So you could have like a square pulse or a sawtooth pulse or anything like that. And those would be energy signals.
One comment I might add is that if you think about the definition, Ryan, if you don't mind scrolling over just a little bit to the left so that we can see those, the non-energiness or non-powerness only comes when we get into trouble with the t equals infinity part. So if x of t, we are of course assuming that all these signals we're talking about are bounded in amplitude, of course, i.e. these are finite amplitudes. But if they also last for a finite amount of time, then it's almost guaranteed for them to be both energy and power signals. So in case of biomedical analysis, it rarely ever run into cases where they're not energy or power signals by the simple fact that most of the signals that we come across are bounded in time as well. So it's kind of silly in that sense, but it still by definition makes sense that if x is bounded and if the limits of the integration are also bounded, then you'll definitely get signals that are energy and power as well.
So, are there any other questions, math questions, conceptual questions, anything of the sort? Alrighty, I am going to hand it over to the next person. If you have any other questions, feel free to drop them in the chat and I'll answer them the best that I can.
Hi everyone, can you hear me?
Yeah, we can hear you, Alpha.
Cool, thanks for joining us again today and decided we're gonna get stronger together. We're gonna ace this class. Okay, so Amelia, I'm not sure that I have recitation up on my screen. Would you mind share your recitation screen real quick?
Are you talking about the PowerPoint?
Yeah, the PowerPoint.
Okay, I can share that.
Thank you so much.
Absolutely.
Okay, so so you want me to cover this transformation of signal, or you want Will to cover this?
I'm happy to do the transformation. I thought that you were going nice, Alpha. Do you want to go?
Oh, I see. Yeah.
Do you want
Yeah, we can go to even and odd function first then.
Yeah,
Okay.
let's do it.
All right. Hello, everyone. Today I'm gonna teach you about the odd and even signals. So let's see what is odd and even. I'm gonna use whiteboard today. Right, and as usual, don't draw random stuff, okay? I'm the only one who can draw random stuff on here. Okay, what is even and odd function? So any signal can be right, any signal is composed of odd component and even component of it. Let's say this. And what is even, like what is even signal and what is odd signal? Let's see this. Okay, so I have an even signal here. And what I mean by even signal is that let me see my cheat sheet real quick. Okay, even function is the function that unchanged when reflected about x-axis. Meaning that if I have a graph that looks like this, this is gonna be even signal, even function, because it doesn't change like when I reflect this part, when I reflect it about the x-axis. Excuse me? Oh, y-axis, everyone. I'm sorry. Yeah, this is y. Thank you, Amelia. Y-axis.
Well, I think what you meant was the intensity axis, and which in this case would be the x, because we have the x along the y-axis, right? Because the function itself is, so I think you meant the vertical axis, right?
Yes, vertical. Let's make it clearer. Vertical.
Yeah. It would not be wrong to call it the x-axis, because now we have two axes, which are the x and the t-axis. We don't have the conventional x and y here. So you were not wrong, Alpha. But I think Amelia was trying to be using the mathematical notation of the horizontal axis always been called the quote unquote x-axis and the vertical called the y-axis.
All right, thank you, Professor, for
Sure.
that. And also, we know the definition of even signal. Let's see the definition of odd signal or odd function. So odd signal is gonna be unchanged. This is the definition that I found on the internet. So please correct me, Professor, if it's not right. And it's gonna look something like this for odd signal.
I would
Here.
say rotate it around the origin by 180 degrees. I wouldn't say x-axis because again, now x-axis, I don't know which axis you're talking about, horizontal, vertical. Either way, a better way is to say about the origin. So if you look at it from the top, and if you were to rotate by 180, then it should look the same. But that's the, I understand that's a perfectly valid internet definition. The way I like to give it is in terms of two transformations. So it is also, you could say that the odd signal is a signal that is unchanged when you do two reflections, one across the vertical axis and then followed by the horizontal axis or vice versa. And that is effectively a 180 around the origin. So even you reflect about the vertical and it remains the same. For odd, you need to reflect it by about the vertical axis and then do a horizontal axis reflection. And if you get the same thing that you started off with, then you have an odd signal.
Thank you, Professor.
Sure, and you might want to scroll down a little bit. I don't think we can see your odd signal. I can, but I don't know if others can.
Yes. Can you see it now?
I can't.
Yeah, and
Am I
I
supposed
think,
to scroll?
student helped me.
yeah,
with
the scrolling's at
Oh,
each
okay.
user's discretion.
Got it, got it.
Alpha, I think there's like an eye in the corner that has like a little lightning bolt on it. If you click on that, you can say like follow, like force follow or something, or like require follow me.
Oh, okay, thank you. I got that. You got that now? I see. Let's catch up with this technology together. All right. And okay, thanks for whoever helped me in adding these equation here too. So this equation also signifying the signal property of being even and odd too. So
One more missing thing is x of t equals minus of x of minus t. You're missing a negative sign inside the bracket.
x minus x of negative t here. Okay. So can we return to the presentation, please? I
Yeah.
need to stop. Okay. Right. Thank you so much.
Mhm.
Okay, so we know the definition of odd and even signals now. And as I say, any signal can be decomposed into even and odd signal. Let's move on to next slide, please. Okay, let's work on this problem. Given the continuous signal xt here, decompose this signal into even and odd components. All right, we're gonna do the whiteboard thing again. Let's do this problem together, everyone. Okay, earlier we know the theoretical definition of odd and even signal. Now we're going to look at the mathematical concept of even and odd signal. Even signal is half of the amplitude of when we add xt together with x negative t here. And also odd is when we have the half amplitude of xt subtracted by x negative t. Okay, and from the problem that we have earlier, I'm gonna draw the graph here. Okay, can you see me, everyone? Can you see me drawing graph here?
Yep.
Cool, okay. So this is, okay. Give me a bit of time to write the graph down here. Okay. I believe this is the xt that we have on our question, right? And oh,
Yeah, that looks good.
cool, so this is correct. Thank you. So this is our xt. Let's start from doing the even function. So when I have xt, I know this is my xt and I'm happy now. But the next thing that I want to do, I want to know what is x negative t. I want to know how is it gonna look like. So how should I do that? Basically, we do this graph by flipping everything down, and it's gonna look like this. And everyone, don't worry if you feel like, oh, thank you for the graph. If you feel like this version might be hard for you to see, I have another version that is more nicely drawn here. Okay, so thank you for the graph, Amelia. Okay, let's draw xt into x negative t. X negative t, as I say, we're gonna flip it down. So it's gonna look, wait. Excuse me, everyone, it's not flipped down, it's reflect with this axis, so it's gonna be this direction, actually. Okay. Okay, and our graph x negative t is gonna look like this. All right, so now we got both of xt and x negative t now. The next step is to solve for, let's start with even function. So for even function, I want to add these two graphs together, and then I will half their amplitude. And it's gonna look like, let's start with adding these two graphs together first. Let's start with adding these two together. So I'm gonna draw a graph here. And one more line here. There is a trick that I like to see how I'm gonna add this stuff. So let's start from the leftmost hand side. I'm gonna look at both of the graph. This thing has the it started 0 here, so 0, and this is -1. So when I add these two together, okay, this is -1 and -2. This thing, if I add them together, 0 add with -1, it should be -1. Okay, and we got this part now, and we're gonna move on the right hand side. Next part, we have 2 here. And this part, we have 1. 2 plus 1 is 3. So next part, I'm gonna have my graph up here. This part, can anyone help me with this part, please? So we have 2, and we have 1 here. And this part, I have 2. What is 1 plus 2 gonna be? Thank you, Will. It's gonna be 3. So the next part of graph is gonna be on 3 too. Okay, this one. Anyone would like to help me with this last part, please? Thank you, Nicholas. That's been really helpful. Okay, so when I have these lines, I'm gonna connect the line together. Okay, and because these has been 0 all the way, they have been 0 all the way, so they're gonna remain 0 here too. Therefore, this is gonna be our xt plus x negative t. Woohoo! We're almost done now, everyone. And our last part for figuring out the even function is to have the amplitude. And it's gonna look like this. There's something that I like to do. When I write this down on my homework, oh yeah, thank you, Amelia. I think I'm gonna do this. Okay. Yeah, I can copy and paste it. Cool. Okay, thank you, Amelia. I think it doesn't. Okay, let's say it's gonna be like this. And what I like to do when I have the amplitude is that I'll just change what I have on the y-axis into half of it. So instead of being 3 now, what is it gonna be, everyone? What is 3 divided by 2? Yeah, 0.5. Gonna be 1.5. Okay, now look at our lower bound. It used to be -1, right? So what is this gonna be right now? Thank you, 0.5, correct. Yeah, so this is gonna be how our even function look like. This is even function.
Now, one thing to do at this point is do a quick sanity check. Remember that the even is symmetric around the vertical axis. So a quick sanity check should tell you, just visually, does it look symmetric? If it's not, then you probably did something wrong. You might want to go back and check your calculations. Okay.
Okay, check that it's symmetry. symmetric on vertical axis? We can do this check to everyone. Vertical axis. Thank you, Professor. Okay, now we know how to do even function. Anyone would like to try odd function with me? Okay, let's do it. Let's do the odd function. And by doing even function, we add xt and x negative t, right? So when we do the odd function here, we gotta do xt subtracted by x negative t instead. Okay, let's draw that, everyone. Okay, let's start on the leftmost side. Here, from xt, I have 0, right? And x negative t is negative 1. So what is 0 subtracted by negative 1? It's gonna be 1, right? So this part of the graph is gonna be 1. Okay, let's move on to the next part of the graph. Can you see my mouse, everyone? Can you see my pen right now?
Yes.
Okay, thank you. You're following me, right? So what is this part gonna be? Okay, I drawn that already. Okay, let's move on to next part. Anyone would like to try this? Anyone? Okay, I'm gonna do this part then. So, the next part we have xt at 2, xt actually at 1, and x negative t at 2. So we're gonna start by subtracting 1 by 2, and that's gonna give us negative 1. Cool. Anyone have question at this part right now? If you feel like you're confused or you want me to repeat or go over any specific part again, please let me know. Do you understand what I'm doing here? If you have any question, let me know. Okay, seem like everyone is cool, then I'll move on. Okay. Can anyone help me with this last part here? Yeah, this last green part. What it's gonna look like on this graph. Okay, so for the green part here, we have xt as -1 and x negative t at 0. So the graph that I want to see is going to be -1 minus 0, which is going to be -1, right? So can anyone help me draw on the graph here? Thank you, Alaya. Okay, that's correct. Okay, it's gonna look like this. So our final graph, not final yet, but xt minus x negative t is gonna look like this. Yeah, so this is what we're gonna get. And remember, this is not done yet. The final step is to divide the amplitude in half. So our graph is gonna look like okay, I cannot copy and paste them right now. Okay, I got it. Cool. So the amplitude is gonna shrink by half, right? Our final graph is gonna look like, so this used to be 1. Now it's gonna be 1/2, or it's gonna be 0.5. And this part used to be -1. Now it's gonna be -0.5. And that's it. Now we got our odd function. Yeah, and we can do the check here too. Yes, and that's it for even and odd function. Can we go back to the slide, please? Thank you. Yeah, I believe that's it for my part. So, okay, I know on whiteboard it kind of look wiggly a little bit, but I have another nicer note version, and I'm gonna post that. Okay, thank you, everyone. Professor, you have any point to add, Amelia, Will, and Ryan? Or
Now,
if
only
you
a
have
similar
any,
point that I wanted to say about the odd. Once you've decomposed into the odd component, just check that it is anti-symmetric. Just visually make sure,
anti-symmetric.
as in, just mentally look at what it looks like and try to do 2 rotations mentally and make sure that it looks same as before you did the rotation. So that's a quick sanity check again.
Cool. Thank you. I'll add that to the note too.
All right, looks like we have a couple of questions. Yes, Jade, works for any signal. So because the way we've defined the even and odd component, it automatically guarantees that you can take any signal and decompose it into odd and even functions. And related to that is the second question from Nicholas, which is what is the point of doing this? What we'll find out is that, this is a neat trick that we end up doing where we decompose signals into sines and cosines. And when you have signals that are even or odd, they have certain mathematical properties that you can, kind of utilize. And so as one example, what we are going to do when we do the Fourier analysis, we'll break down signals into sines and cosines. and that way we will kind of be able to take any given function and then break it up into sines and cosines and do further analysis based on that and utilize the properties of oddness and evenness, and it kind of simplifies the math a little bit. So there's another question, whether the amplitude always shrinks for odd and even functions. I could start off with a made up negative signal where it might seem like it's actually increasing. So that's not necessarily true, but if you always start with a positive signal, then yes, because we are subtracting for the odd part, we're subtracting two signals. So you might end up with a smaller appearing signal. But again, that assumes that you started off with a mostly positive signal, which we did. All the examples we've done so far, we started with but if you start with, like, say, the negative of that, you'll find that that's not necessarily true. Okay.
Thank you, Professor.
Sure.
Okay, so we'll hop right in. Let me share my screen. Okay. Can you guys see everything and hear me okay?
Yep.
Yeah, you're all
Okay,
good.
sweet. Okay, sweet. Okay, so I'll be talking to you a little bit about signal transformations, but before I hop in, I just want to emphasize that the recitation is definitely a time for you guys to utilize, Professor and also us three TAs and Amelia outside of class. So definitely don't be afraid to ask questions. Don't be afraid to interrupt, or, I'm sure if you have a question, there's at least one other person who probably has the same exact question. It's probably the fault of the people presenting, right? Maybe we skipped over something or made it confusing. So, if you have any doubts or anything, please always interrupt or ask in the chat. Okay,
absolutely. And one more point, for
Mhm.
all those who will be watching this as a recording, please consider attending in person. This session is enriched by your questions. So like Will was saying, your presence here and asking questions is what makes this even more valuable thing. Regarding the questions regarding homework, just it's yes, the short answer is yes, but please be mindful of the TA times. They're putting in a lot of time for this session. They have their own stuff to do, and that's why they have separate office hours as well, so that they can address your questions directly there. So yes, if it's a quick thing, I would recommend feel free to ask, and to the extent any of the TAs is able to stay on, we'll definitely answer the question. But please do consider leaving the homework questions for your one-on-one TA things.
Awesome. So, and I also understand that since the session is being recorded, it may be, a little awkward to turn on your camera. So last time I encouraged you to turn on your camera, but this time, feel free to keep it off. Just I highly encourage, you typing in the chat or vocalizing any questions. Okay, so gonna start off with an outline. So we're doing signal transformation. So we're going to go over quickly what is a transformation, just the fundamental, time domain transformations, and we'll do some step-by-step examples. So we're going to start off with some examples just one by one, and then we'll go into some practice problems. Okay. So here are some transformation of signals, and a little bit about why it's important is these are kind of the fundamentals, right? This is the basics of how we can manipulate signals in a time domain. So getting a good intuition about this will help a lot for future analyses, and you also just get a good feel for, manipulating signals in the time domain. So to start off, you guys can see my screen. So we have, as far as the foundations, the basics, we have two general categories of transformations. So we have time-related and amplitude-related. So we're going to start with time-related, okay? And the first one is going to be translation. So we're going to start with that. Okay, so one, translation. So I'm just going to start off with a basic signal here, just very arbitrary. Okay, maybe we can call this -1 and 1. And if we're going to do some translation, we're going to move it left or right. And Dr. Kodabakar has this good saying called you have a right to be negative. So if you have something like x of t minus beta, maybe I can make this a different color actually. Right? We can call this beta 1 just to be extra specific. So this is going to move this entire signal by beta. And if we had something else, maybe x of t plus beta 2, that would shift left by beta 2. Right? So what does that actually look like? So if we want to say maybe beta 1 is equal to 1, okay? So then we have something like x of t minus 1, right? So what we do, the way I like to think of this is we have these 3 individual points and we kind of play connect the dots. So we have these 3 individual points and we're going to subtract or add their x coordinate. So here, we're going to move it right. So we have negative 1, 0. Maybe we can call this 1 or 2 even. Okay, so we have 0, 2, and we have 1, 0. Okay, so what this is going to look like, so we're basically going to shift the entire signal over right by 1. So here, right? So this is going to be 0, and this is going to be 2. So we basically took each individual x coordinate and we added 1 to it. So plus 1, plus 1, plus 1. So now here are our new coordinates. We have 0, 0, 1, 2, and 2, 0. Okay. So how's everyone feeling about that? Any questions so far? So this is only just translation in the time domain. So we move it left to right. We can do another example. Okay, so maybe we can do a little box. Call this 2, 1, 3, right? And maybe let's do the shift in the left direction. So what's that going to look like? So if we want to call this function x of t, this is t, right? What does x t plus 1 look like? So once again, we take our individual coordinates, 1, 0, 1, 2, 3, 2, and 3, 0. And my brain turns off after 4 p.m. So if I make some numerical mistake, please interrupt. And we basically subtract all the x coordinates by 1. So here we're going to go minus 1, minus 1, minus 1, minus 1, minus 1. So it's pretty easy to make a mistake. So my best advice is, once again, try and isolate the individual corners or each like node, if you will, and write out their coordinates and just take it step by step and then plot all the points individually. And then you can play connect the dots. So using that method, maybe we would see something like okay, so then everything here, I'll draw it in purple. Okay, so here, actually, yeah, we'll do connect the dots here. So we have 0, 0, and then we have 0, 2, we have 2, 2, and then we have 2, 0. Okay, so now we have our 4 nodes, and we kind of connect them like this. Okay, so that's translation. Everyone feeling pretty good about that? Okay. So now we're going to hop into the next transformation. So we just finished translation. Now let's actually go over some reflection now. So reflection or time reversal. So if we have some arbitrary signal x of t, once again, here's the y-axis. My lines are not very straight here, but bear with me. Okay, so when we have a negative t here on the inside, that's going to be a time reversal, and that's going to be basically flipping it over the y-axis. So we're going to be flipping it like this, rotating around here, 180 degrees, right? So if this is x of t, this might be x of negative t, right? Here, this is going to be -1, -3, and like that. So how, once again, how I might solve this is doing that same exact thing. So kind of try to isolate these nodes or these points and then play connect the dots. So if we have 1, 0, we want to call this 2 maybe. Then we have 2, 2. And then we have 3, 0. So we're basically just times all these by -1, times by -1. And we don't, so this does not affect the y coordinates at all, just only the time domain. So we're only affecting these t coordinates, might be more accurate. So then these coordinates might read something like, whoops, -3, 0, -1, 0, and -2, 2. Okay. How's everyone doing? Can I get a thumbs up emoji or anybody have any questions? It'll just only get more confusing if I keep going. Okay, I'm getting a lot of thumbs up, no questions. All right. Okay. So now we're going to go into time scaling. Okay. I'm going to try to go just a little bit faster because we have to get out at 7:30, and I think the practice problems will be most useful. Okay. But it's still important to go one by one because it's only going to be pure chaos if we get into combination. So basically the whole point of this is to show you one by one what each one of these transformations look like, and then show you how they can be combined together. So if we don't understand them individually, it'll be very hard to combine them. Okay. All right. So now let's go into time scaling. Time scaling. Now, what does that look like? Okay, so let's do another triangle. I really like triangles. Okay. So actually, maybe it's a little bit easier to do something like this. Yeah. So intuitively, maybe we're all familiar with frequency, right? So if this is x of t, and let's say we increase this by some very large number. So we say like x of 10t, right? And this is just some sine wave. And we're all pretty used to seeing it go a lot faster, something like this. That's very horribly drawn, but right? So this is conceptually, we increase this number here, this is going to get faster. It's going to have an increased frequency. But what that looks like from a signal transformation perspective is actually a shrink, right? So here we're kind of condensing this. Maybe I can use a different color. We're kind of condensing this into this, right? So overall on the same time axis, because this is still 1, right? This is still 3. So we're kind of shrinking everything together. And if we have the opposite, so this would be a shrink, right? And this would be a stretch. And here I'll show you what maybe x of 1/10 t looks like. And it's going to be, very, very drawn out. Okay. So this is still 2. Might look something like this. And these are not to scale or anything, but just so you guys get the concept, right? So we have a smaller value, and that's going to be a longer stretch in the time domain, right? Okay. And it's very important. We'll come back to this, but this will be important later because it's actually the exact opposite of amplitude scaling. Amplitude scaling, we'll see when we increase this number, we'll see a stretch, and when we decrease this number, we'll see a shrink. But we'll get to that when we get there, okay? Actually, I guess it's the next one. Okay, amplitude scaling, perfect. So now we're moving on from time-related transformations to amplitude-related transformations. So we're no longer dealing with the horizontal axis or the t domain, time domain. We're now going to be going into the vertical axis, so the actual amplitude of the signal. Okay. So if we want to use that same example, or a similar example, I suppose, and this is 2, and we'll call this x of t. We're going to see that 10x of t, so now this 10 here is on the outside. So it's no longer on the inside of the parentheses. So all the time-related transformations are going to be inside these parentheses. But now that it's outside the parentheses, it's going to be dealing with amplitude. Okay? So inside parentheses, time domain, shifting horizontal axis left to right, stretching and shrinking on the horizontal axis. When it's outside the parentheses, it's going to be the vertical axis. Okay? So what this is going to look like is now right now these are still the same. So the x-axis components don't change, but they're going to be much higher values. It's not exactly a scale, but okay, so now this would be 20. So if we want to use that similar metric of going node by node and then connecting the dots, this would be 0, 0, 1, 2, 3, 0, right? So now when we're outside the parentheses, we're working in the amplitude, we want to basically alter our vertical coordinate. So here, amplitude scaling, it's multiplication. So we're going to multiply this by 10 because it's 10 here. So 2 times 10 is how we got that 20, okay? So if we're going to do that, we would see 0 times 10 is still 0. So that's why this is 0, 0. This 1 doesn't change. But now 2 times 10 gives us that 20. And here, once again, it doesn't change. Okay. How's everybody feeling so far? Can I keep going? Let's see some more thumbs up. A sea of thumbs ups. Okay, we're looking good. If I start speaking nonsense, just interrupt me. Okay. So now we're going to get into the offset and reflection. So we're going to do, once again, these same things that we did earlier. These reflection in this translation, but now we're going to do it along the vertical axis. So we break them up into separate components, separate transformations, and then we can combine them later. We'll see that in the practice problems. Okay. So now let's do amplitude offset. Okay, so now if we want to call this x of t, right? X of t. And now if before we were adding, when we're shifting left and right on the horizontal axis, we were adding inside the parentheses. But now we can add something outside the parentheses and it'll affect the vertical axis. So plus some arbitrary, we can call it just b, okay? And what this is going to do is it's just going to additively add to the coordinates. So once again, with our going node by node, point by point, this is 1, 0, 4, 0. We want to call this 2. This is 2, 2. We're basically just going to add b to all these vertical coordinates, plus b, plus b, plus b. So if we want to call b equals to 3, then all of a sudden we have 1, 3. We have 2, 5. And we have 4, 3. And then we can just connect the dots. Okay? So no multiplication, this is adding. Okay, and then on the same note, going into the reflections. This is going to be the last of our 6 properties, okay? At least for now. Okay, so our last property is if we now have a negative on the outside. So we're going to multiply by -1 on the outside. We get something like negative x of t. Now we're going to flip around this x-axis. So here we're going to flip around here. What that looks like if we go node by node So we have 2, 0. We have maybe 3, 3. And we have 5, 0. So now we're going to multiply all the y coordinates by 0. So here, multiply by -1, multiply by -1, multiply by -1. We're going to get something like this. Okay, and here, actually, yeah, doing our node strategy, 0 times -1 is still 0. So this is still 2, 0. And here, 3 times -1 is -3. And then, once again, 0 times -1 is 0. So we have 5, 0 here. Okay, everyone follow me so far? Oh, Nicholas, I love that see a thumbs up. I know you're killing it right now. Okay. So everyone feeling good so far? All right, we've only got 10 minutes left, so hope everyone's following me. I'm gonna hop right in, and I want you to interrupt me if you have any questions. Okay, so now we have all these different 6 transformations. We can shift, we can scale, and we can reflect. And we can have a time domain and an amplitude domain. So 6 different things we can do. So what does that look like here in these combinations? So this is what I like to call standard form. I'm not sure if it's standard form in any textbooks, but at least standard form for this class and the methods we're going to use in this class. So here we can say, so normally we'll see that A's and alphas are associated with multiplication, and we'll see that normally betas and B's are associated with adding or subtracting, right? So what's really important here is actually the order in which you do everything. So I know this is mind-breaking stuff, but trust me, guys, if you don't understand these basics, the rest of the class becomes very hard. So if you're crushing it now, that's excellent. Just keep crushing it. But if you're struggling with it, then just keep practicing, and I promise you'll get better. And come to us for help and lean on us. So my favorite acronym for this is actually, it's called BAB. So I kind of pretend that I'm a lamb or a goat or something, like Bob, Bob, and that's the kind of the order I do things. Okay, and then I know people get confused. Bab. Okay, is it this way or this way? I like to think number 1 is Bab, and number 2 is like the Greek letters come first. So these beta, alpha, and then A, B, Bab. Okay, so the order we're going to do things is okay. So let's say we have this standard form, right? Let's say we have the worst case scenario. The worst case scenario is that we have all 6 transformations. And I don't know if you'll get a problem like this in the homework or on the test, but it's just good to know. And have this list next to you when you're doing the homework, and do your best to use BAB, lean on BAB. So if we have negative A x of negative alpha t plus beta plus B. So here we have an amplitude reflection, we have amplitude scaling, we have time reversal, we have time scaling, and we have time shifting, amplitude scaling, right? Okay, so the actual order you're going to want to do these things. So the first step, so we're going to start in the parentheses, is how I like to think of it. If you forget BAB, just start in the parentheses. And so the first thing you're going to do is use beta. So we're going to time shift. And normally we do all the time stuff first. So focus on all the time, and then we'll get to amplitude. So you know that you're starting with these 3 things first. Okay. And the second thing is then we're going to do scaling. So we're going to do alpha, we're going to do scaling. Okay. And this is where it can get kind of tricky, right? So after we scale is when we're shifting. And I'm not 100%, reflecting. I'm not 100% sure if the order matters, but just follow this format and you'll never make any mistakes. So, yeah. So then we have negative alpha. So this is the negative sign. So then we have this reflection in the time domain. So here we have our time domain. So we start with the time domain. We do it in this order. Actually, we're always in the time domain, but maybe time axis is a little more accurate. Okay, and then we have time scaling. So now we're not doing it in the same order, which is why it can be a little bit confusing, right? It's not like we go time shifting and then this fourth one is amplitude shifting, right? It's in a different order. So the order is super important, and if you do it in the wrong order, you will get a different answer. If you don't believe me, you can go on Wolfram Alpha and play around and try to do different, combinations of things, but you will get different stuff. So just do your best to practice, and I promise you'll be successful. So now we'll do scaling. So now we will do alpha, or excuse me, A. So now we're into actual regular letters. Amplitude scaling. Okay. Then we're going to go into amplitude reflecting. And then we're going to do the offset last. Okay, so I know that was a lot. And this is also known as DC offset, by the way. DC offset. Okay, so I know there's a lot. We're not going to actually use, there's no problems here that have all 6, but this is good to keep for your reference, okay? So we only have 6 minutes left, so I'm actually going to start with the harder problem because I think you'll get more out of that. So here, let's say you're given this problem, right? This is definitely a problem you're going to see on the test, or not necessarily on the test, but in general, right? You're going to see some, what I mean by a problem is you're going to see some formula like this and then some signal like this. That's what I'm referring to, not this exact problem or anything, but this is a similar format in which you'll see later. That's what I was trying to say. So the first thing you want to do is make sure it's in BAB format. Pretend you're a goat or a sheep. Okay, get into BAB format. So we have x of t equals ax alpha t minus plus b. Okay, and I know it's a little thing, guys, but this is actually flipped from this. And I mean, I know it's a little thing. I'm sure, I would just follow this format, get into this format. It's just one little switch, and I promise you won't make any mistakes. So it just takes one little mistake and the whole answer is wrong, right? So let's first start to rewrite this. So let's call this x of t. We can call it actually maybe x1 of t. Okay, so x1 of t. We're just going to rewrite it real quick. So we're going to have minus t over 2 plus 4 plus 2. Okay. Okay, so we're going to get it. And so the second thing I like to do is actually write out what we have to do. So we have 6 things that we can do, but we don't necessarily have to do all of them, right? So then I like to write out what we have to do, and then we'll actually do it. So the first thing we want to check for, right, in BAB format is, do we have a time shift? So here we have one. So we'll have the time shift. And can you guys type in the chat whether you think we're gonna, we'll have the time shift by 4, but do we go left or right? Which direction do we time shift, guys? Right. Oh no, I'm correct. Yeah, we're going left, but yeah. So we're gonna be going left, and the reason we're gonna be going left is because we have a right to be negative. Right to be negative. Right to be negative. So it's positive. So we're going left. We're gonna time shift by 4 points left. Okay. The next thing we check for is, do we have, right, we're going to go toward this here. The next one we have is amplitude scaling. So do we have an amplitude or an alpha value? What I mean is there a coefficient of 1 or is there a coefficient of not 1? So here we see there's a coefficient of 1/2, right? We can even write that to be a little bit more clear if we wanted to. Minus 1/2 t. So this way we make no mistakes. So now we're going to have to time scale by 1/2. And is this going to be a shrink or a stretch? Stretch, yeah. Shrink or stretch, guys. So remember, when we increase that, it's going to go a lot faster. So if it's going to go a lot. Right, exactly. Yep. So because it's a longer value, a smaller value, it's going to have a lower frequency. So it's going to take longer. It's going to stretch out. So we're going to put stretch. Okay. And now, is this coefficient positive or negative? It's negative. So that means we'll have to also do a time reversal. Okay, cool. So now we've officially finished everything we have to do for the time domain. Time axis. We're always in the time domain here. Okay, so now we've crossed out this. We've crossed out this. So now we're into amplitude. We're in the last 50% of bad. So now on the outside, do we have any coefficient? Is this 1 or not 1? Well, it's not 1. So we're going to have to amplitude scale by 2. Is this a stretch or a shrink? Negative alpha is a reflection. Yep. So time reversal is the same thing as reflection. Yeah. Exactly. You're right on point, Megan. And we're going to go a little bit over time, guys, but if you don't have any plans, I'd highly recommend staying to see how we solve this out. But if you don't have time, no worries. Go ahead and head out and we'll post the recording online. Yep, it is going to be a stretch. Right, so these are both actually stretches, which can be confusing, right? Because this one is greater than 1 and this one is less than 1, but they're both stretches, right? Okay, so now, is this positive or negative? This 2 on the outside, right? It's positive, so we don't have to worry about this 5th step. So we don't have to even worry about there's no amplitude flipping or anything. And then we're going to have to offset by 2. So where do I get that? It's going to be from this, right? So we're in the last thing of B. Right, and just to be extra clear, guys, so this way we make no mistakes. A, negative alpha, this is going to be beta, and this is B, okay? So this offset by 2, are we going up or are we going down? It's positive. So you're going to add plus 2 to all the y coordinates, right? So you're going to go up, okay? So now let's actually work out the problem. So even if they give you this x of t, guys, I still recommend like rewriting it out. So let me pull it up on my computer so I don't have to keep going up and down. Okay, so here, okay, and we're probably gonna go around 10 minutes over, guys. So if you have to dip, no worries, it's gonna be recorded. But I highly recommend staying. That way, if you have any questions, we can answer them directly here. Okay, so here's your signal. So we want to call this -3, -2, -1, 1, 2, 3. So we're going to have a point here and a point at -2, 1. And -1, 2. And it's going to plateau over here. And then it's going to go to 1, 1. And that's going to go straight down 1, 0. Okay, so this is our signal, guys. So even if they give this to you, I'd highly recommend just to redraw it out. That way you have it, okay? So let's go back up here. We've already written what we have to do. Now we just have to do it, right? So first we're going to time shift by 4 points left. So if we want to use our method that we've previously identified, -3, 0, -2, 1. I know it's tedious, but I promise you, if you do it this way, you'll get 100%. Very little room for error. You're decreasing your odds for making a silly mistake, okay? So 1, 0, 2, -1, 2, 0, and 3, 0. And this is kind of a mess. So if you prefer to write it, over here and do it like that, that's probably cleaner and better, but this is how I've done it. So, okay. So first we're going to time shift by 4 points left. So what does that entail? We're going to add +4 to all these x coordinates here. So +4, +4, +4, +4, +4, +4. Okay, so all of them. And then we can, we can just simply replot those exact points, right? So this does not affect the y-axis at all. And we're going to have, oops, this should be -4, right? Not +4. It's +4 in the parentheses, but it's going to be -4 on the coordinates. Nobody caught me in the comments. You guys are all losing 5 points from your next test score for not catching me making a mistake. I was actually testing you. Okay. You guys are being penalized. I'm just joking. Okay. So here, -7. So we're going to have -7, 0. Okay, so we're going to have -7, 0. We're going to have -6, 1, -5, 2, and we're going to have -4, 2, and we're going to have -3, 1 down here like so. Okay, and then we just connect the dots. That was my favorite game as a kid. I'm just joking, it wasn't actually. Okay, so then this is officially time shifting by left. So here we might want to call this x of t, right? And here we can call this x of t minus 4, right? Or +4, +4. What am I doing? So it's very beneficial to write it like this, step by step, and then also write what you're actually doing. So here, if you write this on the homework or the test, you've identified, which step you're doing. So doing it step by step is much easier than doing it all at once. Okay. Okay, so we officially finished this time shift, right? Boom. So now we're on to amplitude scaling. Or wait, we wrote it somewhere else. Here, yeah. So time scaling by 1/2. So we're going to stretch this, and I'll teach you guys a little trick, okay? This is what I like to do. So you basically write the same exact thing, okay? And all you have to do is change the axes, right? Because you're changing the entire axes. It just gets a little tricky, okay? So you have to pay attention to what you're doing, but here we're stretching it out by 2, so we're time scaling by 1/2. So we can just multiply all of these by 2. So this would become, okay, what am I doing? Okay, let me do that one more time. Sorry about that. Copy. Okay. Okay, so here, -14, -12, -10, -8, -6, -4, -2. So how did I do that? Is everybody okay with how I did that? So basically, we're stretching time by 2. To multiply the entire thing by 2. So what you could also do, so this is one avenue. One other way you could do is to, I'm going to erase this in a sec, so don't worry, but we'd have points from -14 all the way to, -2, and then we could just have it, visibly stretched out. But in my opinion, then you just get a little bit low on space, and it's a little bit easier just to kind of turn off your brain and just multiply the whole scale by 2. Because this is visually the same exact thing, it's just we change the scale, right? Okay, so we finished this. Nice. Now we're going to do time reversal reflection. So does everybody remember how we did this? So if we're going to do the node method, we're going to write out all the points. What do I have to do, guys? I'm time reversing it. What is this step to do, guys? How can I do this? How do I perform a time reversal? Does anybody know? If I have all these coordinates here, -12, 1, does anybody remember? Flip across vertical axis. Nick, you have earned your 5 percentages points back. Isabella, yep, great job. Okay, perfect. Well, okay, Isabella, we have to get a little bit careful there. Inverse is not the same as multiplying by -1, but I think I know what you mean. So Isabella, I think I know what you mean. You just mean to multiply by -1, right? That's a little bit different than inverse. Inverse means to raise to the -1 power, but flipping means to multiply by -1, right? So just a little notation thing there. Okay, cool. So now we're going to multiply all of these by -1. So all by these, I mean the x coordinates. So on the sake of time, I'm not going to write all of it, but just I'll do 3. So we're multiplying just these x coordinates, not everything else, just these x coordinates by -1. So now by flipping it across the vertical axis, we'll get something like this. Okay, 2, 4, 6, 8. Okay. And now we're going to replot these points. Okay, so 14, -12, 1, -10, 2. No. See, guys, that's what happens. You don't do the node method. You make silly mistakes. You just witnessed it here firsthand. Okay. So now 4, 1. Oops, 4, -1. Okay, and -2, 0. So it's going to look something like, got a point there as well. Something like this. Okay, everyone follow me so far? Okay, so now, right, I kind of skipped this step, which was not a good step to skip, but I forgot to write out exactly what I was doing. So here, we time shifted to the left by 4, then we stretched by 2. So here, this becomes x of 1/2 t plus 4. And now we time reversal, so this becomes x of -1/2 t plus 4. Okay, so just 2 more steps to go, and these ones will be a little bit faster, so bear with me here, guys. So now we're going to amplitude scale by 2, right? So we're going to stretch it by 2. And another trick, guys, so this is the same thing, right? 1, 2. So what I can do, if you don't have an iPad, I'd highly recommend grid paper. As you can see, I have grid enabled on my iPad. If you have an iPad, use grids. If you don't have an iPad, I'd highly recommend investing in grid paper. So then here, we will have 2x, right? I believe it was 2. Yep, so 2x here. So we're stretching the whole thing by 2. And instead of redrawing the whole thing, we can kind of just change these to 2 and 4. Everyone follow me? So I stretched it, but it looks the same because I changed the scale, right? Okay. Everybody understand how I did that so far? Let's get a sea of thumbs up. See some thumbs up. Okay. So the last step here, guys. So now we're going to do an offset by 2. Okay, cool. Offset by 2. And this would be your final answer here, guys. It's the last step. I'll draw it in bright pink. Okay. So now we're going to have 2x of -1/2 t plus 4 plus, I think it was 2 again, right? Yep, plus 2. Okay. And now what we will do, guys, is we're going to take this graph and just add +2 to all of the y-axis coordinates for each point, +2. I won't write it there. Okay, +2, +2, +2. Okay, so the whole thing gets shifted up. We don't change x at all. We don't do any stretching. Okay. Right, so going point by point, we get 2, 2. Okay, we get 4, 1. And then we get 4, 2. We get 6, 6, 2, 6, 3. That's my height. Just joking. We get 8, 4. We get 10, 4. We get 12, 3. And 14, 2. So something like this, guys. This will be your final answer. Okay. me just double check the answer key too. Make sure I didn't fumble. Okay, everyone feeling good? Okay. So thank you for tuning in today, guys. And yeah, feel free to let us know if you have any questions. I'll post this onto the Canvas. And yeah, please feel free to ask any questions. Anybody have any follow-up questions or anything? Feel free to email us or Amelia or Professor or come to our office hours or anything. Okay, guys? Okay, cool. Thanks, Jade. We honestly need that. Thanks, Jade. You're promoted to my favorite student, even above Nicholas. Nicholas, you can have second place. Okay. All right. We appreciate you coming, guys. Your enthusiasm and your, taking the initiative to come here on a Tuesday night at 7:45 p.m. It's going to pay off in the long run, I promise. Okay. So that being said, if you guys don't have any other